All right, so let's continue here. So you guys you started talking about rationalizing to get rid of the 0 over 0, right? When you have indeterminate form. Okay, so here's another problem where you have to rationalize. So when you plug in x equals 0 here, you get 2 minus, root 4, which is 2, over 0, 0 over 0. And whenever you get 0 over 0, that's called indeterminate form. And you have to do some algebra in order to get rid of, the situation that gave you that problem. So we're going to multiply this. We're going to multiply this by the conjugate. Okay.
How come?
Yeah.
How come for C?
Yeah.
It's like it was the bottom, but for this one, it's the conjugate of the top.
Because you have to rationalize whichever side the root is in.
Oh.
Yeah. Yeah.
Oh my God! This just clicked.
Yeah. So here, yep, you do limit as x approaches 0. And so the part where the root was, you're always going to get an a minus b, a plus b situation, right? So use the shortcut like you did last time. Square the first term, you get 4, minus square the second term, and that just gives you what? X plus 4 over x times 2 plus root x plus 4. So so this is where, listen.
Why is it not x? I thought it'd be the denominator that you go off.
Okay, so look, this is where the root was. Okay? We multiplied by its conjugate, and that's where you do a squared minus b squared.
Oh, true.
The other part of it, don't multiply it in, just write them next to each other. X times 2 plus, don't simplify it. Don't. I know you want to, but don't. So now, let's simplify this part. Distribute the negative. 4 minus x minus 4. And then eventually, what do you have left over there in the numerator? Just negative x over, huh?
Yeah, 30% of people forget the 35 to 40.
Oh, you guys watched the other screencast. There's going to be some overlap, and it wasn't a random number. It's between 30 and 40 for sure.
Do the stats.
Oh.
This isn't just calc.
So now negative x and positive x the x's will cancel. So I have the limit as x approaches 0, negative 1 over 2 plus root x plus 4. Now I can actually substitute the 0 into the problem, right? Into here. Because you have negative x on top, positive x on the bottom. The x's cancel, but the negative stays.
You don't need to drag the x into the denominator. Else
Right, exactly. Yeah. So now that when you plug it in, you have negative 1 over 2 plus 0 plus 4, which is 4 in here. Negative 1 over 2 plus 2 is 4. Okay? Okay. So, one more thing. So listen. As long as you are doing the algebra, that limit symbol must stay. If at any of those 3 highlighted parts, you drop the limit, that's minus 1 automatically.
Oh no.
However,
because there's a rad.
Because you're still in expression mode, you're still calculating the limit. But as soon as you substitute the value in there, you can no longer put a limit symbol here, because now it's no longer a limit, it's a value. Okay? All right, question, and then we got to move on. The x is canceled. You see how in the green they canceled? This x and this x canceled. Right here.
So where do you need to exactly remember to put the limit?
Okay.
What's under the radical? X plus 4, right?
Oh, I plugged in a 0.
Oh, okay.
Yep. Okay, you have to have the limit symbol every single step. You drop it as soon as you substitute your value into the expression. Okay? Like as soon as I plugged in the 0 here, the limit dropped. Okay?
Can I ask a what if or not?
Let's finish and then we'll do that. Okay? Okay. So, limits at infinity. Again, when we have limits at infinity, right? This is when x approaches infinity. So again, this is end behavior. Okay? Graphically, when you just look at the graph, you just look at what happens to the y values at the ends of the graphs. But when we're talking about, when we have the functions, then all you have to consider is, so suppose you have f of x is equal to 5x to the 7 plus 3x cubed plus x squared, right? And now suppose you want to find the limit of this as x approaches infinity. Okay. Well, if you want to find the limit as x approaches infinity, now your x value is huge, like a billion. How many zeros does a billion have?
A lot.
9 zeros, right? So, a billion to the power of 7, now that's 9 times 7 zeros, 72 zeros. That's a big number.
What number has a billion?
But now, if the billion is cubed, now you only have 27 zeros. Compare that to like 70 something. Do you see how the two of them aren't, they can't even compare how big this is compared to this?
Yeah.
Which means when you're evaluating a limit at infinity, these lower exponents, they are negligible, is what we call them. So the only thing you have to worry about is that highest exponent. Okay? So, take a look here for a minute. You have to evaluate this limit at x approaches infinity. Okay, you throw these away. You only take the highest exponent, the term with the highest exponent. That's 4x to the 6. So now, if you plug in a positive value in there, your result will be positive, correct? So this is positive infinity or dne. Okay? Here, the term with the highest exponent is this.
Oh, we were getting for positive.
So, yeah, I'll talk about that in a minute. So here, when you plug in a negative number, the negative number will be cubed, so it'll be negative, but there is already a negative in front. Total, in the end, it'll be positive infinity.
Oh, right. Yeah,
Okay.
negative.
Every time you have infinity, positive, negative, or just infinity, you have to also put in dne. Okay, here. The highest term is the term with the highest exponent is 4x to the 5.
Little trickster there.
Yep. Evaluated at negative infinity, will that give you a positive or a negative value?
Negative.
Negative, so this is negative infinity dne. Here, it's negative x squared. At infinity, negative infinity.
I'm guessing you always want.
Oh, no. Yes, negative infinity. Haha.
Wait.
You always want to.
Okay. So, infinity squared is positive, but negative in front of it. Okay. You know what? I just said something that was not mathematically very accurate. In fact, let me talk about this for a minute. I don't ever, I should never see a student plugging in infinity.
No.
Oh.
So we would never do
Oh my God.
infinity to the power of 4.
No.
You can never write that, or like e to the power, like we cannot
You have to erase
do
it.
that.
You
You have to erase it.
You have to erase that.
Yep.
Erase it? Okay, fine. I'll
We
erase
talked about that 2 chapters ago.
We did.
You would come
Good.
to our house and
Yeah.
yeah.
Yeah. Okay. No, I won't do that. Okay.
it. Erase solve
She'd
it.
want us to solve it.
Okay.
Infinity, she doesn't work there.
So look, okay, all right.
Erase the ones where you plug in infinity.
You can never write infinity in an operation, like infinity times 3. That is not allowed at all.
The Roosevelt correlation.
Okay, well, I need to
That was
fix that up
written,
on my home.
as a
Okay.
revision of the non-result.
So, listen. Limits of reciprocal functions, right? So if you have y equals 1 over x, okay, so let's just think about this for a minute because this skill is an important skill. 1 over x. As this denominator gets infinitely large, what happens to 1 over x?
Closer to 0.
It gets closer and closer to 0. Is everybody okay with this? Okay, so this is called a reciprocal function, right? So as x gets very large, 1 over x is practically 0, all right? Okay, so keeping that in mind, what happens when you have rational functions at positive or negative infinity? We've done this before when we did asymptotes. All you have to do is compare the degree of the numerator to the degree of the denominator. So you take the term with the highest exponent on top and the bottom, and you compare. If the numerator has a lower degree than the denominator, okay, so the denominator has a higher degree, then the limit is just 0. So for example, here the leading term is x squared, here it's x cubed. When they cancel, you're going to end up with an excess of x's on the bottom.
Is this like less
And
than the numerator?
Yeah, it's exactly that. And as the x's on the bottom go to infinity, the whole thing will equal 0. So this is just 0. There is essentially no work here. That's it. Okay?
I feel like we learned this.
We have, when I just said, when we were doing asymptotes.
Right, yeah.
Okay. When the degrees are equal, you just take the ratios. So,
Exactly, we did this all during asymptotes.
negative 2x cubed over 6x cubed.
1/3.
They're the same, so it's negative 1/3.
Negative one, yeah, negative. Yeah, I was gonna say, I remember this.
Yeah, okay. So when the numerator has a higher degree than the denominator, like x to the 5 and negative x cubed, now you have an excess of x's in the numerator. So you're going to end with negative x squared, right? That's going to be like the limit as x approaches infinity of negative x squared, right? Is that right? Which is equal to negative infinity. Okay? All right.
Wow.
So,
That's crazy. Who came up with that?
okay.
This word.
So, look here. Okay, so here we have a constant over x. So what is that going to be equal to? As x approaches infinity. 0.
Nice.
What about this one?
That is going to be, oh my god, I should know this by heart. That is going to be
Negative infinity dne. Higher numerator, higher denominator in the numerator.
And this one's 7/2.
Higher, okay?
Is it negative instead of positive?
Because it's negative 3x squared over 5x, so it reduces to like negative. Here, they're the same, so it's 7/2. Okay? All right. So let's talk about piecewise functions. This is like, okay. So piecewise functions, on the homework for number 70, that was using a graph, which we will go over. But here, what you have to do algebraically to evaluate piecewise functions, you have to evaluate the left hand and the right hand at each partition. So, look at this. You want the limit as x approaches 3. And look, the partition is exactly at that same point, isn't it? Right? So, the way this function looks when you graph it is, you have 2x plus 7 to the left of x equals 3, x squared minus 1 to the right. So what you have to do every single time is this. It's a two-step process. Limit as x approaches 3 minus, okay, of, it's this function, right, on the left-hand side. And you just plug in 3. What do you get? 13.
Who is the calculator?
Okay.
Oh no, of course you didn't use it.
The limit as x approaches 3 from the positive side of this 9 minus 1, 8. You see how they're not the same? So the limit does not exist.
Awkward. Where did you get 13 from?
You tell me.
Oh.
Okay.
How do you, oh, never mind.
Okay. So here, the limit as x approaches negative 1 from the minus side of this function. What is this?
Negative 1 from the minus side, that would be x squared minus 2x.
Yep, x squared minus 2x. So when you plug in the negative 1, you get 1 plus 2, 3. But from the positive side, negative 3 plus 6 is 3.
Yeah.
Since they're the same, the limit is 3.
Let's go.
Is it always like from the negative side it's the one on top? Or does
It might be switched. So, like, because this is x less than negative 1, that's to the left.
Okay.
Yeah? Okay.
Wait,
Mm-hmm.
second, the limit was from negative 1?
Yeah, because, okay, so here it's asking you for the limit as x approaches negative 1.
Yeah.
But at negative 1, you want to look at, at negative 1, you want to look at the function to the left and the function to the right. So the way that function looks is, at negative 1, this one is graphed like to the left of it.
Yeah, I get the first one, just the second one, I thought it would be x approaching positive.
No, because you have to, so it's like this, right? This is how the function looks,
Whoa.
right? So you're looking at negative 1. You're looking immediately to the left and immediately to the right. Immediately to the right, the function is 3x plus 6. So that's so negative 1 from the left, negative 1 from the right. Okay. All right, now. Okay, so let me go to number 6. The width in millimeters of an animal's pupil is given by this. Okay? Where x is the illuminance of light shining in the pupils measured in LUX. Look, this is the unit for illuminance. We don't really need to know any of the theory behind it. Write a limit to describe the width of the animal's pupils when the light is at its minimum illuminance. Then find the limit and interpret your results. So we want the light to be at its minimum illuminance. What was illuminance? X. Okay? X is the illuminance of light. So it's how much light is in there. Well, what's the minimum amount of light that could be in there? 0, right? So basically what I want for this one is the limit as x approaches 0 of d of x. Notice also, you can never write limit as x approaches 0 equals to something. It always has to be the limit of a quantity. So this is the limit as x approaches 0 of that mess. 152 x to the negative 0.45 plus 85. And then this one. Whoops. Okay. Okay, now, for this one, let's do a little bit of, let's do a little bit of algebra here.
Love it.
So you have x to the power of negative something, right? Why don't we write it in more standard form? So let's write that as 152 over x to the 0.45. You see how that's the same? Plus 85. Here, 4 over x to the 0.45 plus 10. Okay, so what is it that we're doing here? We want the limit as x approaches 0. Okay, what happens if the denominator approaches 0? What happens to the fraction?
Divided by 0.
So it's not DAE,
Undefined.
it's infinite. It's infinitely large, right? So imagine, right? So you have one pizza, you're sharing it with 3 people. Think about how much each one gets. Now you're sharing it with 2 people, you each get more. One person gets more. So as that number gets smaller and smaller, then the fraction blows up. So the way this stands now, I can't evaluate it because 152 over a very small number is about infinity. So I can't evaluate that. Okay, that's fine. Let's do some more algebra. Limit as x approaches 0. What is this? Let's do a common denominator. 152 plus 85 x to the power of 0.45 over x to the power of 0.45. Okay? So I'm just going to do a common denominator. So I'm just going to multiply this by, x over x to the power of 0.45. Same thing on the bottom. The denominator is going to be x to the power of 0.45. And the numerator is going to be 4 plus 10x to the 0.45. Okay, now, what happens to this and this?
It cancels.
It cancels. So what I have is this. 152 plus 85, x to the 0.45. 4 plus 10x to the 0.45. Now, can I plug in 0 for x? I can. I can plug in 0 for x now.
How come now? Like what's...
Because before I had an x in a denominator and I couldn't have divided by 0. But now I don't, because if I plug in a 0 here, it's 152 plus 0. 4 plus 0.
But wouldn't it have been 10 plus 0 in the beginning or no?
Where? No, because it would have been, if I put 0 here, it would have been 4 over 0, which is undefined.
What about like right in the beginning?
Again, it's to the power of negative, so it's divided by. Like, right? So it's 152 over 4, which is 38 millimeters. So what does that mean? Interpret the results. That's the most important part. What happens? D represented the pupil of this animal, the width of the pupil. And now as the amount of light gets reduced to the minimum, to practically 0, okay, the pupil will dilate to 38 millimeters, right? So as the light reaches a minimum of 0, the pupil will dilate to a width of 38 millimeters. Okay? All right. So now, let's see what happens on the other end. Now it says, write a limit to describe the width of the animal's pupils when the light is at its maximum.
Did you do infinity?
Now x is going to approach infinity. Right? So now I want the limit as x approaches infinity of d of x. But look, let's be wise about this. Hey, put your cell phones away, please. Okay, so let's be wise about this. Since I've already worked to reduce my function, to simplify my function, why don't I start where I've reduced it rather than reinvent the wheel? So I'm just gonna start with this step, right? So this is the limit as x approaches infinity. 152 plus 85, x to the 0.45, 4 plus 10x to the 0.45. And what did we learn about when we have to evaluate a limit, a rational function at infinity? What do we do? Yeah.
The x's are the same, so it's 85 over 10.
Exactly. You just have to compare the highest term with the right? So that's just 85 over 10, 8.5 millimeters.
Use the coefficients.
Yep, because the exponents are the same. Tell me what that means. Interpret your results. Yeah, go.
As the light reaches a maximum of positive infinity, the pupil will, what's the opposite of dilate? Shrink?
Shrink or contract, yeah.
Contract to 8.5.
Exactly. And we know this, right? When there is too much brightness in the room, your pupils will get smaller, they will contract.
Right.
And if there is very little light, they will dilate in order to take in as much brightness as possible. So
as the light reaches a maximum.
So as the light approaches, okay, so here is where maximum illuminescence,
That'd be a good reference.
right? The pupils will contract to a width of 8.5 millimeters. Okay. Look at the keywords here. The light is a maximum. The pupil contracted to a width of 8.5 millimeters. Do you see the mathematical language there? That is important. The rest of it, the actual construction of the sentence can vary as long as you have the important words. And this, to be able to find a quantity and then to be able to describe in English, in a coherent sentence, what you have found using mathematical language, that is where we're headed, where you're headed next year. All right? Okay. All right, here we go. More of the same. Woo! So, with these, two things are very, very important. One is, okay, so two things are very, very important. One is, you should understand that as x approaches infinity, 1 over x approaches what? 0. This is extremely important. Okay? Once you know this, that's really what's important, right? That's really what's important. The rest of it will just fall into place. But that higher denominator means smaller fraction value. That's important.
They ask questions like that on the SAT, very simple.
Yeah. Okay. So, in molecular theory, the root mean square speed. Are you guys in AP Chem? No? Okay. The root mean squared measures the average speed of a particle in a gas defined by this formula. You don't need to have any knowledge of anything having to do with molecules and how they travel. We are given a formula. You need, however, to be able to sift through the words and understand the relevant information. Okay, R is a constant. T is temperature. M is the molar mass of the gas particles in kilograms per mole. Okay, now, you want the limit of V as M approaches 0. First, we're confused. But you can't just sit there and look at and stare at the page and just remain confused. You have to take action, right? The first thing is write down something to get like the brain juices to flow. Okay, so now you look. What the heck? Okay, this is the limit as M approaches 0. Oh, I'm given V. So now we stare at this and we're like, wait, have we made things better or worse? Well, maybe we made it better, because what am I being asked for? You want the limit as M approaches 0. So, no pun intended, 0 in on the M. Where is the M?
Plug it in.
Right here.
Plug it in.
What happens? Nope, don't plug it in. What happens as M approaches 0?
It'll get bigger.
Infinity.
The whole thing will get infinitely
Whoa!
large.
Beautiful.
So this is going to be infinity.
We're too good.
Okay, now we need to interpret the answer. Okay,
This is my favorite part.
this is the average speed of the particle. Okay, V is the average speed. M is the molar mass. So, somebody tell me in English, what's happening here?
Okay.
Okay.
So, as
Mm-hmm.
hold on, wait. Let me organize my thoughts.
Mm-hmm.
Oh, I think I get it.
Okay.
So it's saying as the molar mass shrinks, the speed is growing infinitely.
Exactly. As the mass of the particle approaches 0, the velocity will become infinitely large. Okay? So as the mass of the particles approaches 0, the velocity becomes infinitely large.
Plug M to 0 exactly to get the ND.
And that makes sense, right? As something becomes smaller, it will like gain speed. Like intuitively, that makes sense. Okay. Now, limit. Find the limit of V as M approaches infinity. Okay, so the limit as M approaches infinity of the same thing.
I already know.
What happens now?
It's gonna be 0.
It's going to be 0. So now if you have a pizza and you're sharing it with an infinite number of people, how much does each person get? 0, right? So this is 0. Okay.
Everybody gets 0.
Oh yeah, that's just that's just.
Tell me what that means in words.
You know, as the mass approaches, as the mass of the particles approaches infinity, the velocity becomes 0.
Exactly. So as the mass of the particle gets infinitely large.
We learned this before, I feel like, in the last one about asymptotes too, about how whenever you put the infinity as it's always approaching 0, but you put 0 down, it's always.
So the velocity approaches 0. And so think about that. That makes sense as well, right? Approaches 0, right? If the particles get infinitely heavier, right, they're obviously going to slow down. Okay? Okay. All right. So let's stop here.